Thank you. I think I need a microphone. Thank you. So hi, everyone. Good morning. I am Ashi, and I'm going to be your guide today as we explore the world of deep learning in JavaScript, which is a world that's growing very fast and yet still very squishy and still very much being born. So I want to start by saying that I am not a machine learning expert, but my mom is, or I kind of think she is. She designed digital filters for hearing aids and then later worked on a speech recognizer at Carnegie Mellon. I worked in her lab one summer, and I remember seeing all of these very strange terms and very unfamiliar sigils all over the wall. And learning this stuff has kind of brought me closer to her. Because the other day I got to tell her, hey, Mom, I have finally learned and understood what cross entropy is. And by the end of this talk, hopefully you will too, at least well enough to use it. So I've been learning deep learning kind of as a hobby, out of curiosity, with some excitement for the future, and also with a certain sense of deep and abiding dread that the robots are coming and they're going to take all our jobs and possibly also consume our societies and maybe ourselves. And I have some good news on that count, which is that the robots are very impressive and they are getting more so every day, and they are also still fundamentally quite stupid. They're probably not going to take your job, at least not for another year or two. But they are going to change it. And so now is a very exciting time to be getting into the field. There's a lot of tools that are becoming available for us in JavaScript to work with machine learning. And there's a lot of new research that's happening as well. So let's dive in and survey the landscape. And to start with, I'm about to say the word tensor like 500 times. And many of you probably know what it is, some of you don't. So let's get on the same page about that. So a tensor is just a block of numbers, as we'll be using it. There are other deeper mathematical explanations, but for our purposes, it's a block of numbers. So a rank 0 tensor is called a scalar, and it's just a single number. Rank 1 tensor is also known as a vector, so it's kind of a line of numbers. Rank 2 tensor is a rectangle of numbers, it's a matrix. Rank 3 tensors are kind of number rectangular prisms, and so on into shapes that are harder and harder to illustrate. So this is useful because tensors form the basis for all of the mathematical operations we do in machine learning. We are going to be taking chunks, these number chunks, and flowing them between different operations using a library called Tensorflow. So TensorFlow comes in two flavors. Actually, it comes in several flavors now. There's TensorFlow Python, which is the sort of traditional library that most machine learning researchers still use. That's based on the TensorFlow C++ library. There's also TensorFlow JS, which is designed to run in the browser and run under Node. And now they have TensorFlow Swift, and it wouldn't surprise me if there was TensorFlow JavaScript. All of these are basically the same programming model of a graph of operations that knows how to pass data between these different processing nodes applied in different languages. And they have pretty comparable behaviors. So in TensorFlow Python, we can run our compute graphs on the CPU, on the GPU, and on TPUs. TPUs being sort of special purpose hardware that Google has to train machine learning models specifically. In TensorFlow.js, we can run on the CPU in Node and on the GPU using WebGL. And I believe they are about to add TPU support in Node, but it is taking some time. We have in the Python side of things just a huge machine learning ecosystem. So Python has been where machine learning researchers have been doing their work, and so there's a large ecosystem for it. That is still growing, I would say, in JavaScript. When I first made these slides, I would say it was much more inchoate than it is now. Now there are many, many tools that are starting to come up. We have observable notebooks and other systems that make it much easier for us to experiment with machine learning in JavaScript. And we'll look at some of those today. So what all this amounts to is, in general, when we're training new models, we're probably going to be doing that with models written in Python, but then the TensorFlow ecosystem lets us take those models and run them in the browser with TensorFlow.js. And that's a pretty significant win because it means that we can leverage the power of machine learning. We can build these models, and then we can run them without any connection to the cloud, which means they can be available without a network connection. They can be available without sending users' data up to our servers, which is always nice. It's like a significant privacy win and a significant latency win. So now that we've kind of gone over how we what tools we can use to create models, it's probably worth talking about what models are exactly. Like, what are machine learning models? So say we have a phenomena in the world. That phenomena is going to be this snake. So a model is a way of understanding it. They are versions of the world that have been simplified. So if we wanted to model the curvature of this snake, something we might do is just try a whole bunch of different curves and try and find one that fits. So we might just guess and check, right? We might pick a curve and be like, oh, this curve is not working out so well, let's try a different curve. And we might just keep doing that over and over and over again, trying a whole bunch of random curves and seeing which one is the most snake-like. Now, even for this very simple model, that would take a very long time. What we want is a way to make a guess and then figure out kind of how wrong it is, and then iteratively improve the model so we can take steps, keep taking steps until we find something that's the right fit. And it turns out that we can do that. That's a process called stochastic gradient descent, which, like a lot of terms in machine learning, is not nearly so scary as it sounds. So let's look at another phenomena that we might want to model, like say this splatter of paint. Let's say we wanted to model it as a line. So we wanted to find the line that goes through this splatter of paint as best it can. Incidentally, this is almost certainly not something that we want to do. This is not how we would probably want to model a splatter of paint. But lines are very easy to reason about. They have very few parameters, and so this is the example we're going with. So first, we're going to turn this phenomena into observations. We're going to throw a coordinate system under it. So now we have points, and we're going to perform linear regression on them. So we're going to try and find the line that goes through them. So you might remember the equation for a line as y equals mx plus b. This represents all lines except for completely vertical ones. Here, m is the slope, b is the y-intercept, which means that if we pick some random slope and intercept, then we get a line. Now, this line is not a particularly good line in terms of fitting this data. For example, this point is way off, and these points are kind of a little bit off. We could go through and look at all the points and measure how far off they are. And this gives us a quantity called loss, which represents how badly we've done. How wrong is our model when compared to the data? So there's a number of different ways we could measure loss. A common one is mean squared error, which is the average of the error squared. So if we were to write it in JavaScript, it would look a little bit like this. So our mean squared error loss function takes data and a model and reduces over all of the data points to the sum of the error squared, which means that for any given line, we can ask how well it fits the data now. We now have a number. Now, we're passing the slope and intercept, m and b, into this higher order line function. These are our model parameters. And since there's only 2 of them, we can actually visualize all of the possible models that we have in 3 dimensions. So we'll put m on this axis and b on this other one. And then we can kind of, for any given point, we can ask, okay, how, for any given point in slope and intercept space, we can ask how good are these model parameters at modeling our particular set of data. And then we can figure out which way would make that better. Like, what is the slope of the surface at this point? So here, loss is telling us how to change the model. We're kind of exploring a landscape, and at every point, we're going to try and roll downhill towards a region of the model with better loss. So the slopiness of this landscape is called its gradient. And so this process is called gradient descent. We are iteratively tweaking the model parameters and kind of rolling downhill as we do so, trying to minimize loss. Now, as you might imagine, there's a lot of different ways we might realize this process. For one thing, if we have a lot of data points, computing loss against all of them will be very time-consuming. We'll spend all our time basically figuring out the mean squared error versus all of these error points. And so instead, we can do almost as well by just randomly picking a few points from our data set and computing the loss against those. And so that gives us stochastic gradient descent. And then there's also the question of how big the steps we take are. So we know that at some point, it would be better to have a larger slope and a smaller y-intercept, for example. But we don't know how far we should move in that direction. So the size of step we take is the learning rate. Now these are model hyperparameters. They're parameters to the training process rather than to the model itself. Whereas model parameters are discovered through training, hyperparameters are typically discovered by you tweaking them manually, staring at screens until your eyeballs bleed. There are some better techniques for this, of course, but in the simple case, they're often just things that you kind of guess at and see how our models train. So that's it for a line, fitting a single line to some data. But there's other functions we might use. There's other functions we might want to fit to our data. For example, we might try and fit a sigmoidal function. The reason this S-shaped curve. The reason we might do that is because it kind of looks like the activation function of a neuron, and it might be the 80s, and we might have been trying to find sort of nice, well-behaved mathematical curves that can kind of approximate the behavior of neurons. Or we might take this function on the bottom, this like very sharp function, which is the max of x and 0. It has a spectacularly complex name. It's called the rectified linear unit, because that is how rectified linear units behave in electrical circuits. But surprisingly, this turns out to be an extremely useful function for deep learning, in no small part because it's very, very easy to compute, much easier to compute than the smoother and in some ways mathematically nicer sigmoidal function. And so this bottom function is what most deep learning neural networks use for most of their activation layers. So what we can do is we can take a bunch of these units, a bunch of these rectifiers, and kind of stack them into layers. So this is 2 layers with 4 units each. Now we'll connect them densely, which means all of the units in the output layer connect to all of the units in a given input layer. So the input to this unit is the weighted sum of all of the outputs from all of the units in the previous layer. The weights here are the model's parameters. So they're what we're going to discover through training. And each of the units is just computing this very simple function, the max of x and 0, which means that each one is basically an if statement. And as we're adding additional layers, we're just nesting if statements deeper and deeper. So the number of parameters we have in even a simple model adds up pretty fast. This network has 16 parameters, even though it has all of 8 units. And it can't do very much. But we would already be very hard-pressed to visualize its loss landscape, right? Like, I don't know about you, but I have a hard time visualizing 17-dimensional spaces. And models that are actually useful are much, much bigger. So this is a representation of the loss landscape for ResNet, which is an image classifier that was state-of-the-art about 3-4 years ago. And it has about 60 million parameters. Now, they're obviously doing some pretty heavy projection and simplification to try and draw something that's even remotely intelligible. The actual loss landscape for this 60 million dimensional shape would clearly blow our tiny minds. So now we have this idea of what models are. And the good news is that while it's helpful to know all of this, you do not have to be able to visualize the loss landscape for a very complex network. We don't even have to really know how to train them ourselves, because there are some pre-built, pre-trained modules that we can just npm install. And so let's take a look at one of those. We're going to do some transfer learning. Specifically, we're going to adapt MobileNet, which is an image classifier, to turn Tallulah. Where's Tallulah? There we go. Tallulah, my elephant, into a Pac-Man controller. So that's Tallulah. She's my friendly stuffed elephant. Let's see. Let's go back to training. So the way this works, and the video might not be working right, but let's see, is, yeah. So first, I am going to I'm going to record sort of example images for each of the different ways that I can move Pac-Man. So I'll hold Tallulah kind of up, I'll hold her to the right, I'll hold her to the left. And I'm trying to kind of get different ways for, I'm trying to capture sort of all the different ways I might hold her to give the model a representative sample. So then I click train, and it spends a little bit training the model. You can sort of see the loss drop down. And then we're going to try playing. So you can see that it works sort of surprisingly well, but also not extremely well, especially once I get frustrated and have trouble holding Tallulah in the way that I held her during training. So we're doing pretty well, It's not clicking, yeah, now we're eaten. We just got eaten. And using your friend as a game controller can be hard on a friendship, so I want you to know that we're still friends. So let's take a look at how all of this is working. This is actually a TensorFlow JS example. You can go find it on their GitHub at the URL there at the top. And we're just going to kind of walk through it. So the first thing we're going to do is we pull in TensorFlow, TF.js from TensorFlow, which gives us the sort of base TensorFlow libraries. We load this controller dataset utility, which we'll look at in a second. This is going to help us store all of our example images and then feed them to the training set later on. We load MobileNet from Google Storage. MobileNet is a pre-trained model. It has all of the weights already pre-discovered by being trained on on a large set of images on some Google data center. So we're going to use transfer learning, where we take an existing model and we sort of tear the end of it off and adapt it for a new problem. So the nice thing about transfer learning is it's much, much faster to train a model using transfer learning. You get basically most of the true facts about image classification that this model has already discovered, but then you can adapt the actual image classes at the end for a different problem. So what that means is we're not going to return the full model from this load MobileNet function. Instead, we're going to return sort of an internal layer, this conv pw13 relu layer, which we'll look at in a second to figure out what part of the model that is. But it's kind of a layer near the bottom. So now we're going to go through the process of adding examples. So whenever we add an example to represent up, down, left, or right, we're going to add it with the controller data set. So the X value that we're using is the output of MobileNet. So that's what transfer learning means, right? We are going to run the image through MobileNet until it gets to that layer, and then we're going to pick out the activations of that layer and use that as the training example for our much smaller network that we're training. And then finally, we can go and train our model. So it's a sequential model, which means it's just a list of layers all wired together. The first layer is going to flatten the entire output of MobileNet into a rank 1 tensor with 12,000 elements or so. Then we're going to throw in a densely interconnected layer. So dense layers connect to every single output of the previous layer. And we can kind of customize the number of dense units in the UI. The default is going to be 100, and that works pretty well, unless you're trying to control Pac-Man with an elephant. And maybe I could have used a few more. There'll all be rectifier units, our friends from earlier. So they're that very simple, easily computable function that nevertheless turns out to be quite useful because it's so fast to train. And then at the end of the network, we're going to have a softmax layer. So softmax is another fairly simple idea with an intimidating name. It produces output that is a probability distribution, which is what we want here, right? I am definitely holding Tallulah up, down, left, or right. Those are the options. And so we want the output of the network to be a probability distribution over those classes. Like we want it to say, well, there's a 30% chance you're holding her upright and a 20% chance it's to the left. It's nonsensical for it to say there's a 100% chance you're holding her upright and a 100% chance you're holding her facing east. That is not a reasonable output of the network. And so a softmax layer guarantees that what we get out is going to be a probability distribution. And it's trainable towards that. So because we know that, when we are looking at the outputs of the network and trying to figure out how to improve them, we know how to adjust the internal weights for a softmax layer. So we create these 4 softmax units, one for each probability class, up, down, left, or right, and we connect them all to the previous dense layer. And now we train the thing. So we're using the atom optimizer, which is a kind of stochastic gradient descent. It's a little bit better than the standard stochastic gradient descent optimizer in that it's smarter about the size of steps that it takes. It's a little bit more adaptive in terms of the learning rate. Then we compile the model, which generates a TensorFlow graph, the sort of internal representation of all of the operations in the graph. We're going to use categorical cross-entropy loss rather than mean squared error loss, which is the thing that I saw in my mom's lab so many years ago that scared the hell out of me. But basically, categorical cross-entropy loss is the loss function you use when you're looking at a probability distribution. So the question here is, if this is the labeled example, so I'm holding Tallulah upside down, and I think that means that the network should be detecting down as the output. And the network instead predicts this. It's like 10% chance of up, 40% chance of down, 50% chance of left, whatever the rest is of right. How wrong is that? Like, it's definitely not right, but how wrong is it? That's what categorical cross-entropy gives us. It gives us a measure of how much the network has confused different probability classes. All right, so then we come up with a batch size. This is just how large each batch of training data is going to be. That's the number of examples we're going to compute loss from at each step. And then we train. Model.fit fits a model to the data. At the end of each batch, we get this callback, and that's how we can update the UI to show that decreasing loss measure. And then when we play the game, we just fetch an image from the webcam, run it through MobileNet, and grab the activation of that internal layer, and then run it through our model to grab the predictions of which way I'm holding Tallulah. And then we go and figure out which class our network predicted was most likely. So we're like, which of up, down, left, and right had the highest probability? And that's the input that we give to the game. And that's how we can play Pac-Man with an elephant. So let's go a little bit deeper into one particular point here. I said that we're grabbing this layer out from near the bottom of MobileNet, and I didn't really tell you what that is or why. So I wanted to go and kind of figure out myself what exactly that layer was doing and why. And so to get a better sense of what is happening there, I just kind of loaded up this model description file and poked around. So let's do that. So this is the model.json file that we pulled off of Google Cloud Storage earlier. It's a Keras model. And it's just a JSON description of all of the layers in the model. So Keras is an ML library that's now integrated into TensorFlow, and it just kind of describes a layered model, letting you sort of specify all of the parameterized layers. And there are a lot of layers in here. So we have an input layer, and then we kind of have this repeating stack of like a convolutional layer, a norm layer, an activation layer, a depth-wise convolution, another norm layer, an activation layer. And this is how most classifiers look, is they have like a ton of internal repeated structure. Convolutional layers show up a lot in these networks, and they sound well, convoluted and maybe intimidating. And they're another thing that's not so intimidating. So in an image classifier, we're going to have some input pixels. And a convolutional layer is going to take those input pixels and run them through a filter to produce an output. The filter is just a bunch of numbers, and we are going to multiply the source pixel values with the value of their corresponding filter cell, and then sum all of those outputs to generate the output pixel. And then we just kind of walk this same filter across the entire image. So this is exactly how Photoshop filters work, or how many Photoshop filters work. It's called an image kernel. And the key thing about using it in machine learning is that that filter is trainable. So this layer is always going to use the same filter across the entire image. And when we train a stack of these things, we get this very interesting behavior that kind of resembles what happens in our brain. And let's open up MobileNet and take a look inside to see what that is. So here, instead of grabbing just one layer, we'll write a helper function to grab a whole bunch of layers. I'm going to grab a sort of selection of some internal layers so we can see what's going on. We're going to compute predictions for all of those layers, map them to their names, and then toss them into the global scope. This is very hacky. This is very hacky just to create this visualization. Toss them into global scope so that we can call it from the console, call draw layers repeatedly, and then paint the contents of those layers onto a canvas. So that's it's pretty hacky, but it's going to create a cool result. All right. So these are a nice selection of the layers of MobileNet. You can play it. So this is actually updating live. Well, not live right now, but live from when I recorded this. It is very, very slow not because we have to compute all of these images, but because drawing them to the canvas is very slow. If I wanted this to be faster, I could probably map them as textures and draw it with WebGL, but I did not do that. But the really cool thing to me here is you can see what's happening in the network as we go from input to output. So the input layers are they look like me, right? They look like different shades of my face. And then as we go deeper and deeper, it still kind of looks like progressively smaller versions of the input image, but we're kind of extracting different features, and we're slowly going from having just a few large images to a whole bunch of images so tiny that they're not even images, but are probability classes. That's what's going to happen, right? At some point, we have to go from a square of input pixels to the probability that there's a dog in this photo, the probability that there's a cat in this photo. That's what the output classes are. And this is how it happens, by sort of having all of these intermediate layers, which increase the number and decrease the size of the activation layers until finally you get down to, for each image class, a single softmax activation that's like, yes, there is definitely a banana in here, or not. And it all kind of looks like a bunch of, crappy Photoshop filters. Like, here's some kind of edge detection, here's another kind of tuning parameter. Because that's exactly what it is. That's what image recognizers are. They're a bunch of crappy, sort of hard-coded Photoshop filters whose parameters you did not have to code yourself, but are still essentially a pile of spaghetti, which I hope makes it a little bit less intimidating. It's kind of the secret of machine learning, right? It's a giant pile of small, simple operations. It's a giant pile of if statements. It's a giant collection of Photoshop filters. It's a big pile of linear algebra that the big win is you didn't have to come up with the hard-coded values. And I hope that makes it seem a little bit less scary, because the world can seem a little bit scary these days. We live in this world flush with information, and our interaction with it is all very heavily mediated, increasingly by machine learning systems, which are not perfect, which have been trained on whatever data we've given them, and just like us, can be pressed into the service of whoever needs them. There's the proof that neural networks are universal approximators. That is, for any function you can come up with, any mathematical function, there is a neural network that can train it, or that can approximate it to any level of precision. And there's sort of an open question about whether we actually have the training techniques to figure out what the weights for such a network should be. But I do think that we're getting there. And I think that if you believe that cognition, that the very processes of our thinking, is a computable function, then we're moving into a world where those fundamental tasks of cognition are things that we can train a machine to do. These are not real faces. You probably figured it out. These were generated by GAN, which is a deep learning network whose loss function is another deep learning network. And the two networks kind of improve upon each other and learn to dream up things that look a lot like people, or like whatever other thing you've trained them to generate are. And this is not Barack Obama. This is a machine learning generated Obama synced to an actual recording of an Obama speech. And of course, there are systems that can generate speech that sounds like anyone as well. So we're kind of in this state where it is technologically feasible to generate video of anyone doing anything, and increasingly difficult to figure out whether those videos are faked. But not impossible, because the very same systems that that generate these fakes can also detect them. And that makes the providence of truth kind of this very and increasingly esoteric thing. It's something that you have to know a lot about these technologies in order to be able to determine. And so how do we cope with that? With a world where we can't trust our own eyes and ears? And I think one way is to ignore it, to say that these technologies are just not that good yet. But if cognition is a computable function, then our societies and ourselves are games. And we're training these systems. These robots are getting extremely good at playing games. I wouldn't despair too hard, though, because in the history of computation, we have these tides. At first, all important work was done on mainframes and like these big machines that you had to go up to. And then processors improved, and so work moved to personal computers. And then networks improved, and so we put everything in the cloud. And now we're starting to see that tide go out again, both as we begin to realize what we've given away and how much power there is in having these centralized databases that know everything about everyone, how much danger there is in opaque boxes out of our control feeding us with knowledge. But none of these technologies have to be opaque. They don't have to be centralized. We can run them in our browsers, we can hold the powers of these robot minds in our pockets, and we can use them not just to create forgeries, but also to detect truth. So we're very much at the beginning. Everything we're seeing today is very promising, sometimes impressive, sometimes scary, but it's all going to look quite embarrassing in the not so distant future, when you can have a conversation with your AI assistant and the memory of your voice will never leave your wrist. Thank you.